Hey, hello, ROS developers, and welcome to a new live class today. So that's super great that you are here today because it happened that last week we had some technical problems and we couldn't do this live class, but today is the day. So finally we solved those problems and we are ready here. And I can see on the chat that everybody's there also ready. Rushir Sharma, Danny Cash, Cheryl, and the rest of the people there that haven't said hi, but hello to everyone. And today, what is the class, the live class today? Today, it's about how to find the hyperparameters in a reinforcement learning problem. So when you want to train a robot in a reinforcement learning problem task, you want the robot to learn that task, then there are a lot of parameters for the learning algorithm that you need to set up. And so how do you set that? Usually manually. And then you have to do a lot of tests. Today, what we are going to see is how to parallelize, how to do this search of the parameters in parallel machines. So you can have different simulations, each one training with the different parameters that you want to test, okay? So that's the subject for today. And so we are ready, as always. How we are going to start? We are going to start by using the ROS Development Studio. And what I'm going to do is to share with you a ROSjet. And this ROSjet contains the notebook with all the instructions. It contains a simulation. It contains some code that we are going to use. So I'm going to share this, and then you are going to open this. You are going to open a link that I'm going to share with you. Okay, I'm going to put this link of the ROSjet on the chat that you have there. I see all the people saying hello, Capute, hello, RJ, hello, everyone. So I'm going to put this link of the ROSjet on the chat. Then you just click on the link, and then a complete copy of the ROSjet will be created for you, and you can start developing with me at the same time. Okay, and now, today, right now. So let's go for that. So let me share with you first my screen so you can see what I am doing to share a ROSjet. So for that, you need to have an account at the ROS Development Studio. That is very easy and it's free. So it is supposed that you have created this previously to come in here, to come into this live class. So I presume that you have it. Still some people joining the class. Hello, Shiri Arul, and hello, Lagan Kapoor. And then, so I am here on my account of the ROS Development Studio. You should be in some place like this. This is my list of projects that I have. And the ROSjet for today is this one here. Okay, so whenever you create a ROSjet here in the ROS Development Studio, you can share with anybody. It's very simple. By just clicking on this button, share ROSjet, and then getting the the link of it. So you can copy the link and then pass this link to anybody. So anybody that clicks on that link will have a complete copy of everything, including simulations, including code, including notebooks, including everything. That's the magnificence of the ROSjet. So what I'm going to do is to share my ROSjet, this one, with you. Let me first shorten this because the chat of Hangout has a problem with the long links. So that's the only reason I'm shortening it. So I'm going to put it there on the chat. Now you have it. Then click on that link that I have put on the chat, and you will get a copy. Hello, Ludovic. Hello, Gianfranco. People still arriving in the last minute to the class. Come on, come on. The bell has started, has sound, so we have to start the class. Come on, guys. Okay, so everybody that is getting late now, get the link. You will get a copy of the ROSjet of today. That is this one here. Okay, remember that we are going to work on searching hyperparameters today. So whenever you have the copy of this ROSjet, go to open the ROSjet. And here you have some description. It's okay. Let's open it. And here we are at the ROS Development Studio. And then the first thing that we are going to do is to open the Jupyter notebook that contains the instructions. So go to Tools and then Jupyter Notebook. I'm going a little bit slow so everybody that is new to the live class can understand and can follow. Okay, so this is the notebook that we are going to follow today in this class. So let's open it. Click on there, here, and you got it. So here it is, the notebook of today. That contains all the instructions that we are going to see along the class, okay? So let's start. Remember that at any time, if you get lost, if you have problems, if you don't understand what is the next step, please ask on the chat. And let me answer you, of course. Remember that there is a small delay between the video that you are seeing and the chat. So the chat is faster than the video. So you have to allow some time for me to answer you. But anyway, you know it, and I see that nobody is saying anything. So I presume that everybody's already got his ROS yet for the live class of today, and you are ready to start. Okay, so let's start. So that's a summary that what I said. So when we are training a reinforcement learning task, what happened is that we need some parameters for tuning the parameters for the learning algorithm, actually. And then how to find those parameters is an art. There are some techniques, but actually at the end, it's a lot of testing. So what we are proposing here is a way of parallelizing that testing. We are going to see on a minute, okay? So that's what you have obtained now, the ROSJet. It's what we call a ROSJet. And I have put here more information about ROSJet because this ROSJet, it was created by me and my colleague, Miguel Angel. And this ROSJet, you can create your own ROSJet in ROS Development Studio. So you can go to this tab here and create a new ROSJet from zero. And you can put your code, you can put your simulations. So if you click on here, you can fill it and then create it. Okay, so now what I'm doing is just providing you one that is already done. And once you have created one ROSJet, you can share with the world. That's the nice thing about the ROSJets. So if you want to learn more about how to create your own, you have here a webinar about this. And RJ is asking, for which learning algorithm do we search the parameters? Oh, yeah, so for this case, it's for a deep Q neural network, but the same process applies to any reinforcement learning algorithm that you apply here on this, on ROS with Gazebo with OpenAI ROS. So that it doesn't matter. The only thing that matters is the configuration file that you will have to write. We are going to see that in a minute. Then for one type of algorithm, your configuration file will have some parameters, and for other reinforcement learning algorithms will have a different reinforcement learning parameters. So in this case, it's a deep Q neural network. It's the one that we have been using in the last live classes. It's just to go faster with the concept. Okay, so let's go. We are going to work for this example with the carpool simulation because it's a very simple example also, so we can see how it works. And for that, let's launch a simulation. Okay, the simulation is being included here in the ROSJet. And for that, you can go to Simulations and then select Launch File. If you select Launch File, then here, select the main.launch file, this one, and then press Launch. By doing this, a new window of the simulation will appear. So you can see here that the simulation is loading. Where is this simulation code located? That's a very good question. I don't know who asked. Oh, nobody. So it was me. Ah, nice. So I'm usually I ask so nice questions. Very good, Ricardo. Good question. So let's answer this question, your question, Ricardo. Then it's on, if you go to Tools, and then you go to IDE option, then you can see here that there are different workspaces. And there is one workspace that is called Simulation Workspace. In the simulation workspace is where we put all the files related to the simulations that we want to launch. And if you go to source here, you will see that there is a Carpool simulation with the Carpool description package that is a Gazebo ROS package here. Okay, so that's the simulation that we have launched here. And you have to have that simulation like I have. Okay, then that's one thing. Remember that this is a simulation that has been included into the simulation workspace, but the ROS Development Studio already includes many other simulations here that are by the off the shelf, so that you can launch for different types of robots. And if you select one of those, then you will launch a different robot with a different configuration, etc. So that's not for today. For today is the simulation that they have included here in the simulations workspace into the ROS yet. So we have the simulation. Let's go. What do we have to do now? Yeah, let's start the training, the basic training for this. So I have created also in the Catkin workspace of the ROS yet here. If you go to Catkin workspace, then source. Let me close the simulation so you can see it clearer. So here in Catkin workspace, then source, you see that there is the Carpool tests and also the OpenAI ROS. So we are going to use the OpenAI ROS packages for training. So that, and it's already installed here, so you don't have to download or anything. Then we have the Carpool test here, and this is a training setup already with the training scripts, the training launch files, and the training config files. And actually, I should have deleted again. It happens to me again. I should have deleted all those files because I wanted you to build those files. But anyway, I always do the same mistake. Is that it's because of the hurrying. Anyway, then for the basic generic launch file that we have to launch here, for this robot, let's launch it and let's make it train this robot. Okay, let's go. So for that, let's go to Tools. Let's open a shell. And then let's launch this command here on the notebook that says ROS launch. Well, we have to do a source first. Let's do this source. And then we have to do the ROS launch. So ROS launch. And by doing this ROS launch, what I'm doing is launching the training of this Carpool. So now there it goes, and it's starting to train, and it's starting to learn. Okay, so far so good. So, but how does it work? Well, you probably already know from previous live classes, but we are going to review very fast. So, in order to train this Carpool, that is still training there. So in order to train it, we have created inside the config file, we have created this YAM file that is called Carpool N1 try_params.yam. If you open it, you will see here the list of parameters that we have been using for training. These are the parameters that are being used here now in the Carpool. And here, the parameters that are being used can be divided into three things. The first thing is the reinforcement learning parameters. Those are the parameters that are related to the learning algorithm. So these are the ones that we call the hyperparameters. And the parameters that you have here, well, it depends on the algorithm that you're using and also on the things that you would like to tune on the algorithm. Because in this case, for example, we are not tuning the structure of the neural network that we are using. This is already provided fixed in the training algorithm here. If you open on the scripts, you have the training algorithm here. Here, you see here's where we create the DQ. Let me increase the size of the font here so you can see better. Yep. Okay, so here in the carpool entry algorithm script is where we create the neural network. And this neural network then afterwards for training is the one that performs also the training. It's using the parameters of this file. Then on the first part of the parameters file, we have the learning parameters, the one that are related to the reinforcement learning algorithm that we have chosen. Then the second part is the task parameters, all this. Well, those parameters, we are putting this here because sometimes you have to tune actually the way that you define the tasks. Those parameters are not related directly to reinforcement learning. So these are just to indicate the conditions of the task. And once you have indicated the conditions of the task, then you should not modify this in order to make it learn better or faster or whatever. It is supposed that these are just the parameters that define your task in the real situation. So sometimes it also requires to have some type of training of testing, and that is why we include them here, the task parameters. But once you have defined these task parameters, then they should be fixed for the next testing. So when we test, those should not be changed, because you will be changing the conditions of the learning. And that's not what we want. What we want is to change the learning algorithm itself on a fixed condition. So I see here some question. We have to run ROS launch command in Kankin workspace directory or another directory. And then RJ says any directory, but source from this dir first. Yes, that's right. And TechDev, he says, can we train other environments too? Yes, of course. There are other videos previously where we have shown how to create your environment, your tasks, your different tasks, and check them. And if you have questions, of course, just ask me the questions if you have in the comments of the videos, or send me an email, no problem. For today, we are going to concentrate only on parallelizing the search of the hyperparameters. Okay, and for that, we have to select a given task, a given simulation, and a given algorithm. Okay? Okay, great. So we have, as I said, on the configuration file, we have the learning parameters. Those are the hyperparameters. Then the task parameters. And then we have the debugging parameters also. Those are for debugging purposes. That's okay. Maybe they will not exist in your case. It depends. This is just for debugging purposes. And that's it. I have included a description here of each of the parameters so you can understand when it is required. Otherwise, it's very easy to understand the parameters. Great. So that's what we have in the YAM config. Then this is the task parameters that I have indicated. And what else? Yeah, so that's what I wanted to stress, that once the task to be solved has been decided, the parameters of the task do not have to be touched. They are set because they are defining the actual task that you are doing. Okay, this is for the task parameters. So it means, hey, we are going to learn a system, a carpool that has a control type velocity, no join position, no effort, velocity. And then with those conditions, minimum pole angle between minus 0.7 and 0.7, etc., etc. And with those number of observations, number of actions possible, etc. So that's the task. Then the learning parameters are the ones that we have here on the top, are the ones that we call the hyperparameters, and that contain anything that is affecting the learning algorithm. Okay, so here, then what else do we have to? Every learning algorithm will have its own set of learning parameters. That's important. Also, that's something that has been asked, for which learning algorithm do we search the parameters? So in this case, it's for a DQNN So a deep Q neural network algorithm. And for that, then the number of parameters are those ones, for example. Given that we have fixed the structure of the DQ neural network. And so, yeah, so basically that for any reinforcement learning algorithm on any application, I mean, on any task, you will have to find the proper hyperparameters. What this means is that maybe those parameters, they are very good for this DQNN and for the carpool. But then when you change a DQN to another example, like the robot that is moving around, then you will have to change those parameters also. You will not be able to use the same values. There are some rules in general, but then afterwards you have to explore the values, the proper algorithm. So how do usually researchers find the optimal hyperparameters, the ones that work the best for the robot? Well, here I put 4 possible methods. One is manually. Manually, it means that, okay, let's try those ones. Okay, what is the result? Oh, it's not so good. Let's try to increase a little bit the alpha, the learning rate, because I think it's using too few of the information, of the new information. Let's increase it. And that's manually. It means like tuned by your eye of an expert. That's one way. Then we have other methods like the grid search, where you use your knowledge about this problem, and then you select like ranges between those you think that the proper parameters will be, and then you test them. Then there is another random search that is similar to that, to the grid search, but well, you use another way of selecting inside the different areas that you have identified. You select a different, you have a different way of selecting the parameters. You use a random algorithm to select them. And then you have Bayesian optimization. That's a more advanced method. I have put here a link to that so you can have a look at how it works. And today what we are going to see is a manual way of doing it. Making use of parallel computers. And that's the test that we are going to do. So we think that we already more or less know the parameters, where are they? So, and then let's do a few searches, a few trials, and see what are the results. Basically, that will be the use. The same thing can be applied with grid search or random search. The same thing. This is for purpose of simplicity. We are using manual search, where we select those parameters to test manually based on nothing, because I just put the parameters like whatever it was you are going to see, because I just wanted to show you the method. Then afterwards you have to apply directly to the problem. Okay, so those parallel computers, we call them gene computers, and you can see that there is an option here on the top of my screen that is called gene computers. And not all of you will have access to the gene computers today. So all you people that are watching this live class, probably you will not have access, because this is only available for the people who has a non-free account to the ROS Development Studio. This is some advanced tooling for programmers, so that's why it's not available for free users. However, I already said on the previous live class that whoever who wanted to test it with me today should send me an email and let me know that he wanted to use it. And those are the people who has done it. So those people on this list, they should have an option here in their screen that says gene computers. For the rest of you, I am sorry, but you can have a look at how it works, and maybe so you will understand better the search in the manual search, and also it's an interesting experience to see how it works, the gene computers in the ROS Development Studio for your future. Maybe it's useful for you in the future. So for those guys, Saif, Rushir, Jinshu, Daniel, and Andrea, you can also follow the same step as me. For the rest, please watch and ask questions in case that you don't see that clear. Okay, let's go, Jen. So how do we use the gene computers to search in parallel with different hyperparameters? Well, what we do, we need to create a different config file for each type of parameter that we want, for each set of parameters that we want to test. Okay, so in this example, what we are going to do is a very simple example. So let's assume that we want to test 3 different learning rates. So for this simulation that is learning here, you see it has already learned. That's super cool. Probably yours has also learned. So it should be there, also learning. And well, so this one, the learning rate is a 0.01. It's a small one, very small one. But we think that we can learn in less steps, in less episodes. So we are going to use other learning rates: 0.1, 0.4, and 0.9. So we want to try those and see if we can learn faster with this learning rate. For example, that's a supposition, okay? We are going to test. That's an example. Great, so for that, we need to create a file like this one for each configuration. So we have to create a file for the configuration of all the parameters are the same, but the alpha, instead of being 0.01, is going to be 0.1. Then another file, a different file, that the learning rate is changed to 0.4. And another file where the learning rate is 0.9. So remember, this is just an example. And you can, in any of those files, you can modify more than one parameter if you want. This is just an example, and we are keeping this simple to make it understand, okay, the power of this option. So let's create those 3 files. But actually, as I mentioned, I already created during my tests, and they are here created. So we have here that file. So I have included here the YAM files for those three points. And actually, there is an error here. Medium learning rate should be not 0.5, but 0.5. Sorry, not 0.4, but 0.5. Here it is. That's an error here. It's just an error on the text describing, not important. So for each configuration, we had to create a config file. And in this case, we call the alpha 1, then the alpha 2, and then the alpha 3 for the 0.9. Then this is the code for each one of those files, okay? And actually, those have been already created by me, and here you can find them here. Let's open it. Let me open, and you can see that the alpha on the 1 is 0.1. On the 2, let's check, is 0.5, and on the 3 it's 0.9, and all the rest is the same values, even if you can change them, okay? So doesn't matter. Great, so we have the 3 files generated here as parameters. Remember that this one that doesn't have a number is the original one. This is the file that we used to train this carpool here. That is already, so we already know that this can work, but we want to move faster. Okay, so that one, we are not going to use it anymore. And let me close this. Let me stop the training of this one. Because I want to show you something later, okay? So let me close it. So now it has stopped the learning, and then everything has stopped here. And yeah, so that's it. So we have the 3 different files, 1, 2, and 3, with different parameters. And what we are going to do is to launch a different computer with the same simulation, the same training algorithm, but configure with different parameters. So we are going to launch 3 different computers. Each one is doing exactly the same training, the same environment, the same everything except for the configuration. Okay, so in order to be able to launch that, we need to create a generic launch file. what is a generic launch file? Well, in order to launch the training for this one that we have seen at the beginning of the class, remember, if you come here, remember that we launched this file here that says start training and dot launch. So this is the launch file that we have launched for starting the training of this carpool. And this file is here. It's included here. Let me open it. Then what does it do, this file? Well, it first loads the parameters and then launches the training algorithm. That's it, nothing more. It's super simple. But as you can see, this launch file, it's loading a specific parameter file. That's the parameter file that we use to train this one. And that parameter file is the one that has an alpha value of 0.01. It's here. Okay. Yeah. So that was the original one. Then this launch file, you can see that is loading this one. So we don't want to have that because it's forcing a specific line, a specific configuration file. That is why we need to create another generic training launch file that doesn't load any parameter file, just launches the algorithm for training. Is that one? Okay, so you should create this launch file generic inside the launch directory. Then it is already created for you here. You can see, so you can open it, double click, here it is. And that's it. You can compare this one with the other one, and you can see that the only difference is that it's not loading any parameter. Okay, so we are there. So we have the launch file done for launching parallel computers. So this is the launch file that we are going to use to launch the parallel computers. Okay, so far so good. Any question? Any observation? Something that is not clear? Okay, so I suppose that everything is working. So let's go and let's launch the Gene computers, the parallel computers that are going to train in parallel. For that, we go here, Gene computers, and then select this option that says initialize Gene computers. Then here we have to select the simulation that we want to use for the training. Then you click here and then select, of course, the carpool description main.launch. So this is the simulation that is going to be launched in all the parallel computers. Okay, you have that. Then the learning algorithm has to be the generic launch that we have created. Why? Because this is a launch file that is launching the training algorithm, but without loading any specific parameter configuration. Okay? And then here we have to indicate how many computers we want to launch in parallel. Well, this number depends on the amount of money that you want to spend, because you are going to be charged per each hour of using one computer. So if you use one computer per 1 hour, you will be charged 1 hour. If you use 2 computers per 1 hour, you will be charged 2 hours. Okay, so for this example, we have prepared this so you can launch up to 3 computers now. So the people on the list, the people that is there, you can launch up to 3 computers. So you can select 3 if you want. I'm going to launch 3 in my case. Okay, then that's it. You have selected 3 computers. So we are going to have 3 different computers for 3 different config parameters. And then you press next. So this is detecting the config files that we have in our system. And it has detected that there are several. So on the first computer, let's select the file that has the number 1, the carpool params number 1. On the second, select the number 2. And on the third, select the number 3. So I have selected here the 3 different config files that we created. Then once you have selected this in this configuration, what is going to happen is that on the computer number 1, there will be a simulation that is a carpool and a training algorithm that is going to be trained using the config file number 1. Then on the computer number 2 is going to launch the same thing, but using the config file number 2. And on the computer 3, the same with the config file number 3. So that is how it is. And that's all. We just press run. And then the system is requesting the computers and it's generating the different computers, sending the simulations, the code, everything to all the computers. And it's going to start training the algorithm, well, the task. And it will give us some message here on the screen when it's starting. Okay, so it says the computers are being initialized, so they are in the process, and whenever they are ready, you will see a message here on the screen. So you can close this and keep doing some other things, like whatever, I don't know. Yeah, so let's review this and see if there is any other question. There is a question here on the chat from RJ that says, in the case of a local computer, you will be not able to parallelize search of the parameter. That is right. Yes. So this is for the ROS Development Studio. It's a feature of the ROS Development Studio. In case that you want to do it locally, you have to manage yourself. So you have to build all this environment yourself. This is the work that we have done at the construct. And yeah, so well, it's done. At some point in time, we should receive this message that says done. It means that all the computers are running. Then we can go here again to the Gene computers. And now you see that there is a list of 3 computers here. Those are being initialized. And this doesn't have, when it has a green stick here, then you will see that those are ready. And what is interesting about the Gene computers is that you see those ticks here, green, it means that they are ready. And what is interesting is that we can see what each computer is running and how the simulation is going. So that's super interesting, it's super cool. I like it very much. So we are going to do one thing. In the meantime, let's launch again. Okay, so now here the screen is doing something. It's launching the scripts, and because it's about to tell us that everything is ready. So let's wait for a few seconds. Speedy Step says, belated. Happy birthday, Ricardo. Great lecture. Love you. Thank you very much, Speedy State. Yes, thank you. It was my birthday yesterday. Thanks a lot for telling me. Thank you a lot. And Don, so our project is running in Gene computers. So let's close it. And now we can see here Gene computers that they are green. So we can select all of them. You see, I select a Gene computer. Whoop, here. And here you can see that we have the 2 different logs. One is the simulation, how the simulation is working on the Gene computer number 1. And second is how the training is working on the Gene computer number 1. So it should appear here, the simulation, because I can see that it's already training. So it's just a matter of receiving the image from the simulation. And there it is. So we have this here that is training. Let's do the same with the other Gene computer. So let's open the second one and the third one. And here there are. So each one is training on itself and doing its own training, and we can see the logs and the result of the simulation, etc. And the good thing is that those are being generated in a different computer. So you don't have to be using this computer that you were programming everything. It's not getting all the CPU load of this, because this is done in other computers in parallel. Okay, so another interesting thing is that we can also launch here the training of our carpool. Let me launch it again. And here is my local machine. You can see that this is a Gene computer because here on the top it says Gene computers. And this is a local one because it says Gazebo simulation running. Great. So this one is also training. So now I have 4 computers training with different values. Also interesting is that you can go to Tools and select here the OpenAI reward chart. And you will see how the different charts are moving for each Gene computer and for each simulation. So you can see how much they are moving forward. Great. And what else? What else? So they are here. Yeah, so they are testing each one of those. They are testing their parameters and seeing which one. We can see in a few minutes which one is the best. And that's it. Then, oh yeah, about the results. Yeah, so it may happen that you do a lot of those parameters. You change the configuration files. You try again. You can do it. So you can come here to the different parameters files and change the values. So let's change this, for example, to, I don't know, to the decay for to 0.02. Then you save it, and then you can go back to the Gene computers and relaunch the scripts. So whenever you see, oh, this is getting better in this case, so let me modify this and just this and relaunch again with a different alpha decay. So I don't want to waste my time. Then just modify here, save, and say here relaunch. By doing this, all the simulations will be relaunched again with the new configurations in the config files. So you can do a lot of tests in parallel very, very fast and get some information about which one is the best. And all the results, so you are going to do a lot of results of tests. Then all the results are organized in this AI workspace directory. You can see that those computers directories have been created where you can see the parameters that you have taken, you have done on the different tests. So that's interesting because maybe you do a lot of different testing, and then afterwards you don't remember which one was you remember which one was the best, but not the configurations. That's very common because you do a lot of tests very, very quick. So by doing this, you can here open the files of the parameters and see the actual parameters that were used. So in the computer 1, we see that the alpha is a 0.1. On the computer 2, we see that it's a 0.5, and on the computer 3 is the 0.9. Also, when the algorithm finishes, the results will be saved here. So you will get on this directory the parameters with its results, everything. And basically that's it, if I don't remember wrongly. So I think it's everything here. Oh yeah, this image corresponds to this one here. It looks like this instance is the one that is getting the best results. No, it's even this one that is about 20. Reward 20. No, this one is getting even more. So it's getting about 80. So it looks like it's this one, the one that obtains the best results. And no, because the original one is still getting more rewards. So still not decided. Still not decided. But, well, it depends on what you want to measure. If you want to measure speed, you want to measure more reward, it depends. Okay, so that's it. Then here I say, okay, thank you very much for your wishes for me. Thank you, thanks a lot. Then we have a Ludovic that says, how can you copy and use the best train Keras model once you know which one of the parallel simulations work best? Yeah, so that's a question that it was answered on the previous live class, on live class number 36. So we especially did this subject on the previous one, even if there is still something to be solved on that class, that there was an error, but it wasn't small error. Have a look at there, and then if you have questions, Ludovic, tell me, and I will answer. And that's it. So whenever you are happy with your results, then you have to terminate your gym instances, because otherwise you will be losing your money on here. And for that, come here and just terminate the gym computers. That's it. It will also terminate automatically if you close this for more than 5 minutes. So if you close the tab, for example, or your computer, then the system will auto detect that you are gone, and then it will close everything for you in any case. Okay, so that's it for all. So before we finish today, please, I would like to ask you that if you like it, the class, if you like it, the material that we have provided to you, please give us a like, a thumbs up here on the video. Beneath the video, there is a thumbs up, and also subscribe to our channel, because we are creating new videos every day, a new video about ROS, teaching how to do simulations, how to solve with ROS connection with robots, how to do many things, different things with ROS-related subjects. And especially, we have also an academy that is called the Robotic Night Academy, where you can learn a lot more about using OpenAI, reinforcement learning with ROS. We have a specific course only for that, using the baselines of OpenAI with ROS. And I have included here a discount coupon of 10% that you can use to subscribe to that academy in case that you are interested. We have many other courses apart from OpenAI, but that's the one more related to the class of today. And you still want to learn more, listen to our podcast. That's a ROS Development podcast. That is very interesting, because we are talking every week with an expert about ROS. And then this expert is explaining us how they do something with ROS. So we learn a lot, because they provide us the guides for the code. They provide us with insights, with ideas. It's quite interesting, the ROS Developers podcast. I highly recommend you. And that is all for today. Today we are early on time. And let me see if there are more questions on the chat. If you have, please put them there. Let me see. So Ludovic says, sorry, this is my first class. I will look. Okay, no problem, Ludovic, of course, just telling you, just informing you. And Danny does, he says, I was going to ask you about the error we got last class. Oh, yes. So you got me, Danny, because I didn't have time to figure out that one. But that's something that is on our list of things to do, of massive list of things to do. So please send me an email, and then we'll follow together that problem, okay? And RJ says, can I ask a question to the last live class? Yes, of course. And then Lucas Figueiredo says, thank you for sharing. ROS is the way. Yes, definitely ROS is the way. And in the construct, then it's even better the way. So it's you're going to go like this, up in ROS. And while I'm waiting for the question of RJ, I don't know if you have any other questions for today. Simulations, my carpools are still training there. And it looks like we have got another winner, because let me share with you the screen. I have one that has raised up to more than 200 in terms of reward. So that's another winner. Let me show you. Here it is. And then, oh yeah, so the problem is that this label, we cannot see if it is the one of the two. So for that, we need to go here to the gym computers and see that is the number 1. 0, I think it is. Yes, so we have to check the number here. This is something that we are going to prove in the future. Then RJ's question is, do you use DQN, but how to save the model from the Q-learning algorithm? Oh, yes. So yeah, in order to do that, then you have to do it manually. So yeah, that depends on how you have created the learning algorithm for that specific task that you want the robot. So if you have a DQN, then the creators of the DQN, that is the Keras, okay, so the Keras package, already has provided a save function for that. And if I remember properly, I think that we added a save function in some of the live class of the past when we were using a Q-learning algorithm. So check all of them because I don't remember right now, but in any case, if there is none, the person who has created the Q-learning algorithm has to provide you with a save function. So if it is not provided, then you have to do it. So you have to see how this Q policy is being stored into the Python program. Maybe it's an array, then you save the array, and then you afterwards, when you want to recover, just reload the array, for example. But you will have to do this work if it is not provided by the creator of the algorithm. That's I understand. That's not super good. But try the Keras, because it's very likely that the algorithm that you want to have, it's already there. Or, well, no, or it is easy for you to create, and then it can provide you some saving functions that you can use. And then Rishir was asking the same question. Danny does, thanks for give us access to the Gene computer. It worked perfect, but I wasn't able to launch the full simulation, the local one. Okay, that's strange. Why not? You just open a shell and then you launch it, like in the same way as you did it at the beginning. Did you launch the simulation, Danny? Then RJ say, I use the example from the cube, but thanks, I will try it with the array. And then Rishir Sarma, thanks for giving us access to the Gene computer. Okay, my pleasure, guys. It's been my pleasure. And that's all for today then. Please, if you like it, remember, thumbs up. And remember that the next week, so it's next week is going to be very special for the live class, because we are going to show you a special ROS that we have been creating for many weeks, trying to reproduce a very important paper in the terms of the reinforcement learning. Well, actually, it's not reinforcement learning, it's deep learning. It's about domain randomization. So we have created a ROS that allows you to train a robot in the simulation and then transfer that to the real robot. So we only have the ROS that allows you to train everything and on domain randomization system. And so we will talk about that. We'll provide a ROS that allows you to generate the training sets, to perform the training, to integrate this with a fetch robot that uses the detection to move the armed robot and pick the object. And so that's it. That's what we are going to do on the next live class. So I hope that you will join me next Tuesday. And thank you very much, everyone. See you next Tuesday. Wait a second. Picture. Let's have a picture together before we leave. Yes, and the other. Yeah, here. Yes. So now you can see how I will post the picture there. So you can see how is the background of these live classes. So see you guys.